because by the end of 1918, Prussia was basically gone from Germany. It was given to Poland because Germany had lost the First World War, and the map of Europe was completely redone. It was just like, the congressional redistricting. It was much more done. And therefore, there were no more Prussians. So let's go to problem number 3. So we have a telephone switchboard which receives an average of 300 calls. So let's start problem number 3 first. But can make only 10 connections during a given minute. Determine the probability that the switchboard cannot handle all incoming calls in a given minute. In a given minute. So what do you want to find? The probability that the switchboard cannot handle all incoming calls in a given minute. What is the random variable x here? X is the number of phone calls arriving in a given minute. It doesn't matter which is this minute. Any minute in the hour will look exactly the same probabilistically, because the Poisson is telling, implicitly says the Poisson model, that whatever happens between minute 30 and 31 and what will happen with minute 59 and 60 are exactly identical. Okay? First, because of independence. Second, because the probability of success in minuscule time intervals of length delta t are exactly equal to the rate of the Poisson process times the length of the delta t. Here we have a Poisson process. So essentially this x is not x, is x 1 minute here, which is like 1/60th of an hour. Look, the rate is 300 calls per hour, and an hour has 60 minutes. So I put here 1/60th to signify that I have minutes. So the rate is 300 calls per hour, rate of Poisson process. And since I operate in a minute, how many calls do we have per minute? Now my lambda, which is what I will use for my Poisson calculations, is the 300 calls that I have per hour. An hour has 60 minutes, per 60 minutes times 1 minute, which is 1/60th of an hour. So you have 5 calls per minute. Now, given that lambda is the mean of the Poisson, that Poisson, x with index 1/60, this is the arrival of the number of phone calls arriving in a given minute. The mean value is 5 calls. So I anticipate that in average, or in any given minute, 5 calls will arrive at the switchboard. Okay? Now, what is the probability that x 1/60 will be greater than 10? That is exactly the probability that the switchboard will start rejecting calls, because it can only accommodate up to 10 calls. If x exceeds 10 calls, then the switchboard will start not accommodating the calls. So this is 1 minus the probability that, I don't know why this is so sensitive today, less than or equal than 10. So this is 1 minus sigma, let's say I goes from 0 to 10, e to the negative 5 times I factorial. So that's exactly the probability, this number. Now, how do we calculate this number? Well, those who have a calculator know how to do that. Otherwise, you can only estimate or just leave it like that. This is fine as a final result. Now, if I ask you, if I don't say anything about the Poisson, as the problem does here, you have to argue why is the Poisson a plausible model? Under which circumstances is the Poisson a plausible model? I may also ask entrapping questions sometimes, like what is the probability that the switchboard will reject phone calls between minutes 30 and 31, and what is the probability that it will reject phone calls between minutes 2 and 3. It's exactly the same. Why? Because Poisson is memoryless. It forgets what happens outside of the time of observation. You only calculate within the window of the time window of observation. And what happens in any time window of observation is independent as long from any other non-overlapping time window. We mentioned that. So these are assumptions that are necessary for the Poisson. So why is the Poisson a plausible model? Distribution a plausible model. For the switchboard. First, rate of phone calls is assumed to be A times T, where T, this A is phone calls per hour, okay? Where T is the length of window, the duration of a time window of observation. So if I start from 0 to T, it's exactly the same. Length of window of observation is equal to T. I expect A times T phone calls in average within this time window, and that would be the rate of the Poisson that I will use. That's exactly what I did. That's exactly how I calculated the 5 phone calls in a minute. 300 phone calls divided by 60 minutes, that gives 5 calls per minute. Why is this? Well, we expect a uniform, we don't, actually this is how we would say, we don't expect peaks, unreasonable peaks of phone calls that will boost the rate much higher to that. So there is a steady arrival of phone calls in average. Second, independence of phone call arrivals during non-overlapping windows of observation. Okay, that's a necessary assumption, and it's reasonable. It's a reasonable assumption because you assume that phone calls do not arrive, for example, as a result of a distress event. There's nothing catastrophic, so everybody's calling in. If this happens, then that rule of independence is violated, because what arrives now and what arrives next are contingent to the occurrence of an event. Therefore, there is no independence anymore. When people are just calling because they want to call, these are not coordinated actions, and therefore they warrant the independence of phone call arrivals, of numbers of phone call arrivals on non-overlapping windows of observation. That's exactly why this is a plausible model. Third assumption, we spoke about the rate, the phone calls. Now, in very short, delta T long windows of observation, no more than one call can come to the switchboard. Which essentially means that you don't expect two calls to arrive at exactly the same time. At most one can arrive at very short time durations. Now this delta T is not going to be 1 minute, it's going to be 1 second or even half of a second. Okay? That's the meaning of what I put delta T here. Yes?
So that's delta T long?
Delta T long. Long. That's delta T long. All right, and this delta T could be 1 millisecond, 1/10 of a second. These are examples of this delta T. Okay? Now, in the recording, you will see that what I say is that the probability of one call during a delta T long interval is equal to this A, which is the rate times the delta T. So it's a very small probability. And you can have 1 or 0, not 2 or more. Okay? That's the characteristic of the Poisson. That's why, in fact, because you have 1 or 2 and linearity, probability of success equal to A times delta T, we call the Poisson, or we refer to the Poisson as a linear model. If we allow that we can have more than one phone call almost instantaneously arriving, simultaneous arrival of 2 or more calls, then the model is nonlinear. And it's not a Poisson model in that sense. Okay? The Poisson model is tied very close to the binomial model. That's why it's very easy and very usable problem. Okay? So that's how we solve this particular problem number 3. Let's go to problem number 6. Here in problem number 6, which is the problem with the horses, you simply want to observe whether the data really fit, the observations really fit the data. Can we model with the Poisson? Can I use the Poisson to model? Why is the Poisson a very plausible model? Because it's a very rare event. So when you have a very rare event, the probability of occurrence of the event in a small period of time, let's say a day, because here we have 20 years, so a day is a very small period of time, that can be my delta t, is very small, and it's almost impossible to believe that two horsemen would be kicked on the same day by two different horses. And the horses didn't go on revolt against the Prussians. At least we have no account of it. Also, if a guy is kicked by his horse, another guy is not going to be by his horse. So we have independence of events. What happened one day does not determine what will happen in any other day in this 20-year-long period of observation. So let's now try to see which Poisson does fit the data. I did it exactly in the same way. I did exactly the same calculation in the problem with the mutations in the recorded session. And the way you have to do it is the following. What is the probability of x equal 0? Well, if x has a Poisson distribution with mean lambda, that lambda is exactly the lambda that we have here in the exponent in the density function. And let me just remind you of this. Look here, you see the probability mass function? E to the negative lambda times lambda to the x. This x is the number of kicks, of horse kicks, 0, 1, 2, 3, and so forth and so on. So if we go back to my stuff, where it is here, what is the probability that we observe 0 kicks? E to the negative lambda times lambda to the 0th power divided by 0 factorial, and all this is equal to 1. Now let's look at the data. The guys who died because they were kicked by their horses. So X, which I want to fit the Poisson, is number of horsemen in these 20 years killed.
Wait, what does this data mean? I mean,
What?
in order to make these numbers work, it seems like one guy has to die 4 times.
No, it doesn't have to die. We have 4 fatalities. We have 4 fatalities. Nobody dies 4 times. You die only once.
Well, yeah, but the sum of the observed frequency.
Yeah, what does mean 4? What does mean 4 fatalities? Let's understand the data, because it may be an amusing question, but it's a right question. It's a correct question. So what do we have? We have 200 observations. What are these? What do these observations mean? The right side of the column. It means how many people, how many times these people were kicked by the horses. Okay, it's the total number of kicks. So 109 times people were kicked, horsemen were kicked, but none died.
But the observation was data from 20 years of
yes.
Like it says in the event.
So the event is very rare. The event is very rare. Okay.
That each horse beats cavalry man exactly once every year.
No. Then I don't think it comes out from that. So what is the probability that a horseman is killed as a result of a kick, by a horse kick, in these 20 years? We have 200 incidents, and we have a period of 20 years. So what do you believe should be the rate? The rate, if you put X number of horsemen killed,
number of fatalities, the total number of fatalities up to that point of measurement. In other words, is it 109 kid measurements without a single instance of a fatality, and then you have one instance of a fatality, and then you have 65 more observations with no cases of fatalities, and then you have another fatality. Is that what this is?
yeah, they had, well, in this, okay, it doesn't explain it very well. I know the, yeah, the way it is, it doesn't explain it here very well, but I know it from another book that basically the story takes precedence, because I think the first one who tried to use the Poisson distribution was this person, Bortikiewicz, who was, I think, a retired military man. And the result that you see here, 1 and fatalities number 4, that was 1 horse and killed 4 men in the same incident. Okay, it just went bananas. Started killing everybody and they had to shoot the horse down. That's why they stopped, basically, the fatalities. The first horseman was kicked, the second one tried to take over to help the injured one who was on the ground, was kicked again, knocked on the ground, then the others go to catch it and finally knocks down 4 people in the same incident. And nobody can catch the horse. So after that, nobody else attempted. That's why you don't have more fatalities. And the horse was shot because they couldn't control it. That's how the incident ended. I've seen this I think either on the internet or in another book. I don't properly recall. But these are basically fatalities per incident. So the question is, what is the rate of deaths resulting from a horse kick? Do they fit a Poisson distribution? Is the Poisson a plausible model?
0.61.
So to find the rate of the Poisson, you look at the data which give you the zero frequency. The zero number of fatalities, excuse me, because you're looking for number of fatalities. X is the number of horsemen killed by a horse kick during a kicking incident, let's say. Let's call it like that. But in the same incident. So that would be 109 over 200. That's the relative frequency, okay? That probability should fit this, e to the negative lambda. So what would be lambda here? Lambda would be the negative logarithm of 109 over 200. What is this negative logarithm? Can somebody give me this? I don't have a scientific calculator.
0.6069, which is very close to 0.61, which is the actual average. 0.69.
0.61, let's say 0.61.
Well, that's exactly the mean of the...
Okay, so lambda is 0.61. Let's see now, does this fit the data for 65? So let's see. The probability that X is exactly equal to 1, what would that be? E to the negative 0.61 times 0.61 to the first power divided by 1 factorial. I can do the calculation in the fraction. It gives you 0.61. Who can tell me the first factor?
The answer is going to be 0.61 probably.
What is e to the negative 0.61? 0.54. So if we multiply 0.61 times 0.54, 0.33 times 200, 66. You see, it fits the data. And so forth and so on.
And if you guys need, take the sum of all the...
So do you see how I realized that these data are fit by the Poisson? This is basically data fitting, what I did right now. This is data fitting, and there is a probabilistic argument, a statistical argument actually, that tells me, that guarantees what is the reliability of this fitting. There are tests where I have the data, I use the plausible model, and then I try to see if that is a reliable model, the way I fit the data. Exactly what I found the maximum, the most likely, the maximum likelihood estimator by doing this particular thing. Okay, so that's solves this problem. And let me go now back to the problem we were discussing before. Let's to multivariate distributions. Let's solve a problem, and we'll do some expectations there and stuff like that. All these nice things. So let's go to multivariate distributions. And teach by an example, essentially. So I'll do problem 5. We have a x and y, two random variables, and here we have the so-called, as we call it, contingency table. The values of x, which escaped, are here, 1, 2, and 3, and the values of y are 1, 2, and 3. It's a toy example, and we have probabilities. No. If that gets 1, then nothing else gets anything else. So that's 0.5, 0, 0. So that's my contingency table. What does that mean? What is this? What is the meaning of this entry here? I leave some space for my marginals. Now, the meaning of this is that the probability of x taking the value 3 and y taking the value 3 is equal to 0.2. And as we say, the joint density at the point 3, 3 is equal to 0.2. And exactly that value is the joint density. Recall, or I want to remind you, that the joint density at x and y gives you the probability that x, the first random variable x, takes the value lowercase x, and that y takes the value lowercase y. That's the joint density. And this table, the contingency table, gives me the values of the joint density, as you see. So what is the probability that x and y take the values 2 and 3 respectively? 0. Which is the entry of the matrix that would give you this? Show me the board, please. Come on. The board doesn't buy you. That's great. I said x equal to 2, y equal to 3. Yes, correct. Okay? Good. So that's the particular position. Okay, now let's calculate the marginal distributions. automatically, where do we calculate the marginals? On this margin, we calculate the marginal of whom? Marginal of y. On this margin, we will calculate the marginal of x. Y, what is the marginal of y? Let's recall the numbers. Marginal, well, I start with marginal of x. This is the sum. We keep x fixed. We sum with respect to y. We sum all the values of the joint density where we keep x fixed and y varies, running throughout all values of x, or all values of y, of the random variable y. So if I do this, in that particular position here, I will put the marginal of y at 1. What is the marginal of y at 1? I add the values of the joint density at the points x, 1. See, I fixed 1. Allow x to vary. So I run all the elements of the first row, and that will give me 0.5. To allow x to run, I have to run through the first row. Likewise, here I will put 0.3, and likewise here I will put 0.2. And down here, what are the values of the marginal of x? Again, the same, 0.5, 0.3, and 0.2.
So in other words, you're summing things?
Yeah, I sum in row and in column. That's why we put them on the table, and we call the table contingency table. If you want to know, if you want to do the so-called sanity check, the column, the final column and the final row should all add up to 1. And that's why we put the value 1 there, and that's why we call the table contingency table. This was a discovery of the Second World War, contingency tables. It's accounting. You want to see that, I think they were using for logistics. So you want to see if the numbers there. If somebody gave you something that is phony, then numbers would all end up when you add the rows, when you add the columns. So you wouldn't be able to find 1 and 1 by adding rows or columns. You would be ending with different numbers. And actually, in this case, they would do this, 1, 1. And they should match. If they don't match, something is missing. So somebody is reporting wrong numbers, trying to make up the numbers look right. Massaging. So these are the contingency tables. Are x and y independent?
No.
Why not?
Because the probability of x is directly dependent on the probability of y. Also, they can only take only the same value.
What is the rule of independence?
That probability of the marginal probability of x is the same as the mean probability of x.
No.
About the same for y. Is that right?
No. The probability, the joint value of x and y, the value of the joint density at xy is equal to the product of the respective marginals. And this is how we find the joint density when you are given that the random variables are independent. So if you look, in the off-diagonal positions I have zeros, but the marginal are never zeros. So you cannot produce the zero as a product of values of the marginal densities. Therefore, x and y are not independent. Is that clear? Is that clear? Okay, thanks. I'm saying these things because I'll be asking for those later on. I might give you another quiz on Thursday in case we've lost that quiz, the old quiz. If we haven't lost it, then it's probability we can put grades at random with a uniform distribution between 0 and 10. How about that?
It's not very likely anybody got 0 points.
Well, it's equally likely that anybody will get 10. Uniform distribution for each one of you. Okay, now here is something very, very important. Okay? The so-called, we've done the marginal, so now I want to go to conditional densities. This is very important to understand. What is the conditional density? Suppose that I have X, but I have an information that Y takes the value 3. I want to see what is the probability model for the values of X. Since I have the information, given the information that Y takes the value 3.
X is free.
Okay? This is called conditional density, this type of density. And it's the conditional density of X under the condition that Y takes the value 3. And by definition, you only care about now the values of X, because it's a conditional density of X. So that X will be a value of the random variable X. It is the quotient of the joint density divided by the marginal density of Y evaluated at the point for which you have the condition, namely 3 here. And this is pretty reasonable because this is the probability. What is this? This is the probability that X takes the value lowercase x, that should be 3 here, given that Y takes the value, and Y takes the value 3, given that Y takes the value 3. So that is nothing else but the conditional probability that X takes the value X, given that Y takes the value 3. That's exactly the conditional density. The conditional density is nothing else but conditional probability when we have discrete random variables. When we have continuous random variables, things are fairly more complicated. Simply because densities for continuous random variables do not represent probabilities. It's the rate, they represent rates in which we accumulate probabilities. So do we understand now the density? So let's find the conditional density of X, given that Y takes the value 3 here. Well, we have to find the values for X equals 0, X equals 1, and X equals 3. Well, let's calculate the first one. For X equals 0, what that should be? This should be the joint density at 0,3 divided by the marginal of Y at 3. Well, let's look, 0,3. Where is the 0,3? Where is the value? X takes the values, it takes the values 1, 2, and 3. That's 1. So it's 1, 2, and 3. Where is the entry 1? The entry 1 is on the first column for X, and for Y equals 3, then we look at this entry here, and that joint density takes the value 0, divided by something which is non-zero, so it gives us 0 here. So that one becomes 0. Likewise, what should be the entry for the second position?
0.
Now, X takes the value 2, but Y takes the value 3, so I should always look at the third row. For X, which takes the values 2, I have to look at the position X equals 0, Y equals 3, which has where the joint density takes the value 0, okay? So I have another 0. And the final one is what?
1.
I have 0.2 here, divided by the value of the marginal of y, which is in the very right column. So, okay, that marginal of y takes the value 0.2 when y is equal to 3. So I divide 0.2 by 0.2, and that's 1. And that's essentially expected, because this is a density function. The values that x can take 0, 2, and 3. The probability that x takes the values 1 and 2, given that y takes the value 3, are zeros. So the third value is the certain value. It has to take the third value with probability 100%. That's the conditional. That's the meaning of the conditional density. Is it clear how we calculate conditional densities? Okay. We're done with the conditional densities. Mean values. What is the mean value of x? The mean value of x is calculated via the marginal of x. So x runs throughout all values of x. So this one here would be x goes from 1 to 3. So we have to look again at the marginal of x. So that sum, what is the marginal of x? We'll look at the fourth row of the table here, 0.5, 0.3, 0.2. So we have 1 times 0.5 plus 2 times 0.3 plus 3 times 0.2. Did I get the probabilities right? Yes. So that would give me 0.5 plus 2 times 0.6. 1.7. So the average value of the random variable x, or the mean of the random variable x, is 1.7. What is the meaning of the mean value here of x? The meaning of the mean of x? It tells you it gives you a value close to where the most frequent values of x. The most frequent values of x, of course, are 1 and 2. 1 is taking you probability 50%. 50% of the times x takes the value 1. That's why you see the value shifted to 1. What is the marginal of y? Again, you have the same thing. It's exactly the same thing. So that will be 1.7. Okay? Now, let's answer the question in the book. This is the conditional mathematical expectation of x, of y, given that x takes the value lowercase x. And actually, let's calculate this. So here I have to use, it's a mathematical expectation. I will use the density. Y will run 1 through 3. Y times, I have a conditional expectation that I must find. So I use the conditional density. So what is the conditional density of y equal to x? Y, given that x is equal to 1. I go here again. Y is equal to 1. What is the conditional expectation of x? X takes the value 1. I'm sorry. So I confused you. X takes the value 1. So what is the conditional here? Let's say, what is this for 1? I have to divide 0.5, which is the probability that both x and y take the value 1, divide by the value of the marginal of x at 1, which is again 0.5, so that would give me 1. So automatically I have that this is equal to 1. I don't have to calculate the other values because the remaining values will have 0. So I have 1 times 1 plus 2 times 0 plus 3 times 0. So that gives me 1. And likewise, if you continue with x equal 2, then you find that this is equal to 2. And the same with 3. Okay? Now, as we mentioned before, x and y are not independent random variables. We proved that they are not independent. So it is valid to examine their correlation. What is the covariance of x and y? The covariance of x and y is the quantity mathematical expectation of x times y minus the mean of x times the mean of y. What is the mean of x? How are we going to calculate the mean of x? Mean of x is nothing else but e of x and e of y. Now, what is the mathematical expectation of x times y? This is done by this. We multiply the function. How do we form the random variable which has the product of the values of the random variables? We simply multiply the values. In general, when you have a let's not use A, let's use G here. If you have a function of two variables, so those are real numbers, in particular, let's say x times y, can be x plus y. What is the mathematical expectation of g, x, and y? That's a new random variable. And why it's new? Why is it a random variable to begin with? Because in the way I have defined g, I create a new random variable by plugging a value of x for the first coordinate and a value of y for the second component. So then I use the formula of g, and that produces a new random variable. Here the product is namely x and y. So what are the values of the product? What are the values of x and y, x times y? Tell me the values. Which values are you going to take? How do we create the values? We multiply. What does that mean here? X times y random variables. It's a random variable which has values, the products of the values by doing all the combinations of the values. So I have to take, x takes the values 1, 2, and 3. Y takes the values 1, 2, and 3. So the product will take all the possible values. 1, 2, 3, 4. Can you take the value 5? Why not? You cannot form 5 as a product of 1, 2, and 3 and 1, 2, and 3. So you multiply 1 times 1, 2, and 3, you have 1, 2, and 3. Then you multiply 2 times 1, 2, and 3, you have 2, 4, 6. Likewise, you can have 7, and then you multiply all these numbers by 3. So you have 3, 6, and 9. 1, 2, 3, 4, 6, and 9 are the possible values of the product. So what is the mathematical expectation of it? By definition, you take the function that defined them, that's a double sum, and you multiply the values of g of xy against the values of the joint density. So here, if I want to do it, which are the non-zero values of the density? Only the diagonals, okay? So that means that this is equal to x 1 to 3. You have x times x, which will give you x squared. Okay, look at the values, 0.5, 0.3, 0.2. When x is different than y, the probabilities of the values of the joint density are equal to 0. So I have 1 squared times 0.5 plus 2 squared times 0.3 plus 3 squared 0.5 plus 1.2 plus 1.8. That's 3.5. What is the mean of x? We calculated, and the mean of y are both equal to 1.7. So what is the covariance of x and y? The covariance of x and y is ex times y minus e sub y. 3.5 minus 1.7 times 1.7. So what is this equal to? .61. Now, that row is called correlation coefficient. And by definition is the covariance divided by the standard deviations, the product of the standard deviations. What is the standard deviation of x? Let's find the variance of x first. The variance of x is this minus the mean of x squared. Well, let's find this. Now I have only x. So what I can do is to work as if I had just one random variable. Which density am I going to use here? The marginal density of x. That's the information about x, the marginal density of x. When you don't want to consider y at all, as I do here, I want only to find the second moment of x, I can use the marginal of x because the marginal incorporates all the information I need. So that will be 1 squared times 0.5. Let's look again the marginal of x. Plus 2 squared times 0.3 plus 3 squared times 0.2, which is exactly what we had before, the 3.5. That's how we got the 3.5. You remember? It's exactly the same computation. That gives me 3.5. So what is the variance here of x? 3.5 minus 1.7 square, which you did before, is 0.61. So what is the correlation coefficient? 0.61 divided by 0.61 square times 0.61. If you work the variance of y, you will find exactly the same things. So this is equal to 1. Very strong correlation coefficient. That means the two random variables are identical. Almost. You can't tell one from another. It's like looking you and your picture. I shouldn't be able to tell one from another. Correlation 1. Is it clear? Any questions?
Is this still all part of that problem 6?
That was problem 5. Oh no, that was part of problem 5. It said show that rho, the correlation coefficient, is equal to 1. So I did the correlation coefficient. I did expected value. I can also ask you to find what is the conditional variance of y given that x is equal to 1. What do I ask here? Conditional variance of y given that x is equal to 1. That would be e of y squared given that x is equal to 1 minus the conditional mean of y given that x is equal to 1. When I write this notation here, I mean expected value of y given that x is equal to 1. We calculated that before. And that should be squared here. Look here at the density, the conditional density of y. Do you remember? Was 1, 0, 0. Same here then. So when I do this, we calculated this, the second guy, this one here. This is the sum of y squared times the conditional density. Do you remember this guy? That was equal to 1 minus 1 squared. Now, in this, all of the, sorry, I'm going up like that. You see the value 0 and 0, those are probability values here. So the conditional density takes of y, given that x takes the value 1, takes the value 1 at 1. So the first term is 1 squared times 1 plus 2 squared times 0 plus 3 squared times 0 minus 1 squared, so that's 0.
Like, what happens to 1? 1 squared times 1 times 2.
Oh, it gives you 1, yes. So it gives you 1. So what is the conditional standard deviation? I don't know why my there's an extreme sensitivity today.
Could you explain how you got 1 again?
That should be 0.
Oh, it's got to be 0? Yeah.
Well,
Martin,
times 1 is.
Martin, I subtract 1.
Ah.
That's 0, yeah. And I'm recording that. That's the trouble. I'm going to edit that segment. So I can kill the proof. The evidence. All right, I'm just tired. So what is the standard deviation? The conditional standard deviation here. That's the square root of the conditional variance. And the conditional variance is 0. Is that reasonable? Yes, it is reasonable. Because you see that when you look at the density function, the conditional density, the conditional density takes value 0 at the values when y takes the value 2 and y takes the value 3. It tells you 100% when the value of x is equal to 1, y will be equal to 1 with probability 100%. So it doesn't allow any variation. Since it doesn't allow any variation in the values of x, or in the values of y, that means that the variance is equal to 0. That's why you observe variance equal to 0. Don't panic. It's just one value that is allowed. The distribution is only there, only one value. Uniform. Any questions? Back down? Like that? Or up?
No, down. No, we'll do one. We'll do the second. That, okay.
Yes?